Hey everyone, and welcome. Today, we're diving into a data structure that, honestly, is the silent hero behind so much of the tech we use. It's called the queue, and it's all about bringing order to what would otherwise be total chaos in our code. Let's see how it pulls it off. So let me ask you a question. What on earth could a printer queue, a web server getting hammered with requests, and a weirdly specific task like generating binary numbers in perfect order, what could they all possibly have in common? Well, they all rely on one simple, elegant idea: waiting your turn. And in the world of code, the queue is the ultimate manager of that process. All right, so here's our game plan. We'll start with the absolute core of it all, the first in, first out rule. Then we'll see a queue in action with a really neat algorithm. After that, we'll tackle a classic interview question, building a queue from its opposite, and then look at a super efficient way to manage memory. And of course, we'll wrap it all up with the key takeaways. Okay, first things first. Before we can do anything cool with a queue, you've got to understand its one single non-negotiable rule. So what is a queue? It's a linear data structure that runs on a first-in, first-out principle. We just call it FIFO for short. The easiest way to think about it? It's literally a line at a coffee shop. The first person to get in line is the first person to get their coffee. It's that simple, and it's that fair. And this one simple idea is the foundation for everything a queue does. You add things to one end, and you take them away from the other. That predictable, orderly behavior is what makes the queue such an incredibly reliable tool for programmers. Now, when we talk about interacting with a queue, there are really only two main things you can do. When you add an item, that's called an enqueue, and it always goes to the back. And when you remove an item, that's a dequeue, and it's always taken from the front. This strict one-way flow is the secret to how it maintains perfect order. Okay, so we've got the theory down. Now let's see how the super simple rule can become a surprisingly powerful tool for solving a real, practical problem. So, picture this problem. You need to generate every single binary number from 1 up to some number n. And the catch is, they have to be in the correct numerical order. So if n is 4, you'd need 1, 1, 0, 1, 1, then 100. How would you even go about doing that? Well, you could try the naive approach, right? Just loop from 1 to n and convert each number to its binary form as you go. It works, but it's not very efficient. We're talking a time complexity of O(n) log n. But there's a much more elegant and way faster solution that uses a queue. And get this, it brings the complexity down to a straight linear O(n). That's a huge improvement. So how does this magic work? It's actually pretty simple. You start with an empty queue and just add the string 1 to it. Then you kick off a loop, and on each pass, you dequeue whatever is at the front. Add that number to your results list. And then, and this is the really cool part, you create its two children by just adding a 0 and a 1 to the end of it. Then you enqueue both of those new numbers. Let's just walk through this for n equals 6. We start with 1 in the queue. We pull it out, add it to our output, and then add 1 and 11 to the back of the queue. On the next step, we pull out 10, add it to the output, and then add 100 and 101. The queue's FIFO nature absolutely guarantees that we're going to process 11 next before we ever touch those longer numbers. See how it's just systematically building them out, one layer at a time? And what we're actually doing here is a brilliant illustration of a core computer science algorithm called breadth first search, or BFS. By processing all the numbers of a certain length before moving to the next, the queue makes sure we generate everything level by level. And for binary numbers, that just happens to correspond perfectly to their numerical order. So cool. All right, time for a classic brain teaser. This is the kind of thing that really tests whether you get queues. What if you had to build one, but you could only use its complete opposite? So here's the challenge. Can you implement a first-in, first-out queue using only last-in, first-out stacks? Now remember, a stack is like a pile of plates. The last one you put on is always the first one you take off. So how in the world can we flip that behavior on its head to make it act like a queue? It turns out there are two main ways to do it, and each one comes with a totally different performance trade-off. First, you could make adding an item, the enqueue, expensive. Every time you want to add something new, you have to move everything to a helper stack, add your new item at the very bottom, then move it all back. This keeps the oldest item right on top, ready for a super fast dequeue. Or you could do the opposite. Just quickly add items to an input stack. Then, when you need to dequeue, you pour everything from that input stack over to an output stack, which reverses the order, and then just pop from there. That big transfer only happens when the output stack is empty, so on average, it's actually pretty efficient. And this gets to the crucial point. There is no single right answer here. It's all about trade-offs. If you know you're going to be adding items way more often than you remove them, you'd pick the one with the fast enqueue. But if you're removing things all the time, the other approach makes more sense. It completely depends on the job you need it to do. Okay, let's move on to our final and most advanced problem. What happens when you don't just need one queue, but you need a whole bunch of them, and you're really tight on memory? So imagine this. You have to implement, say, k different queues, but you've only been given one single array of size n to store all of their data. How can you pull this off without wasting a ton of space? Well, the simple approach would be to just chop up the array into k smaller, equal-sized chunks. But that's incredibly wasteful. You could easily have one queue that's totally full and overflowing, while another one is sitting right next to it, completely empty. The much smarter, optimized solution is to let all k queues share the entire array as one big dynamic pool of memory. And the key to making this work is something called a free list, which is basically its own little queue of all the empty slots available in the array. The toolkit that makes this possible is it's really ingenious. You've got your main data array, of course. Then you have a couple arrays to track the front and rear of each of your k queues. But the real magic, the secret sauce, is the next array. It does double duty. If an element is part of a queue, its next entry points to the next item in that specific queue. But if a slot is empty, its next entry points to the next available empty slot, forming a linked list of free space. And that free index, that just points to the start of the free list. This design is so elegant, it means any queue can grab any available slot from anywhere in the array. There is absolutely zero wasted space. Queues can grow huge or shrink down to nothing, and the whole system just dynamically adapts. It's maximum memory efficiency. All right, we have covered a lot of ground here, from the absolute basics all the way to some pretty advanced stuff. So let's boil it all down to what you should really remember. Just remember these 4 things. 1. Queues are all about that strict FIFO rule. First one in is the first one out. 2. This makes them absolutely essential for any algorithm that needs to process things level by level, like breadth-first search. 3. Trying to build them from other structures, like stacks, really forces you to think hard about critical performance trade-offs. And 4, as we just saw, advanced implementations can solve really complex resource management problems in an incredibly space-efficient way. At its heart, the queue is a beautifully simple tool for managing fairness and order. Whether it's a simple line of print jobs or a complex memory system, it brings a predictable, calming structure to what would otherwise be total chaos. The only question left is, what complex problem will you use it to straighten out next?